We move on to another important application, which is the solenoid. So if you have a single loop, single current loop like this, the magnetic field due to this loop will be going this way. We determined that from the right-hand rule. The curving of the four fingers represents the direction of motion of the current. So the thumb represents the direction of the magnetic field. So eventually a single current loop is just like a magnetic dipole, as we see here. This would be the North Pole and this will be South Pole. So we may use more than one coil. In that case, we get a solenoid. So the field at the center of the solenoid can be calculated. We are using this approximation method, as if we have four wires. Each wire will have a field in mu naught I divided by 2 pi r. For such wires, we multiply by 4. We simplify 4 cancels approximately with pi. So it's 4 divided by pi is 1.27. So the result is mu naught I over 2r approximately. If you have n such terms, you just multiply by n to get the magnetic field. Okay, this is what we have for a solenoid. We add the magnetic fields due to each one of these terms in the solenoid. They add up, superposition principle. Outside, the field is so weak, we can assume it to be 0. But inside the solenoid, the field is so dense. Okay, so in this regard, a solenoid is very much like a magnetic dipole. It acts like a magnetic dipole. And the magnetic field at the center of the solenoid is equal to naught Ni. N is the number of turns per unit length. The number of turns per unit length in the solenoid. Among the many important applications for solenoids is the beam optics that we use to steer the beams of charged particles. Like in this old style cathode ray TV set, we have a beam of electrons. We can control the direction of motion using electromagnets to steer the beam in any desired direction as it falls on the screen. The same technology is used in electron microscopes. Electron microscopes are sophisticated technological instruments that are used in advanced research to allow us to see a single cell. So here we use a beam of electrons in the electron microscope rather than a beam of light in optical microscopes. And to steer the beam of electrons, which is a beam of charged particles, we use electric fields and magnetic fields. So this is another application of the solenoids. This is another application where we have a monster coil that creates a field that allows us to confine the charged particles in the plasma research so that the plasma will be confined in this space, will be forced to remain in this space using the magnetic force, which is pointing inward. This is how we may derive the magnetic field equation for a solenoid applying Ampere's law. If you take any closed path like this path here, so the field for this segment and that segment cancel each other. The field outside is assumed to be 0. So we end up with just this segment inside the solenoid. So here inside the solenoid you have B multiplied by L, the length of this side. So B equals mu naught Ni divided by L. and N divided by L is the density of turns, number of turns per unit length, which is this small n. This is the simple equation that we have for the solenoid.